good metaphor to describe shared control is horse riding. When a human rides a horse, they can indicate the general direction and speed at which they want to travel. The human does not need to control each individual leg of the horse, instead they give high-level commands. The horse then interprets the human's intentions and moves its own legs accordingly. Together, the horse and rider perform shared control. How does this relate to robots? In robotics, we can use the same principle of shared control to share the control of a machine or robot between a human operator and a computer program or algorithm. A user provides input, for example using a joystick, and the robot gathers information about its surrounding using its sensors. By blending the user's signals with data from the robot's sensors, the system can decide on actions to perform. Shared control has lots of applications, including aeronautics, smart automobiles, and prosthetics. As part of the CrowdBot project, a team at UCL have been researching the use of shared control to assist with driving powered wheelchairs. Our smart wheelchair is a specially modified powered wheelchair, instrumented with an array of sensors. The sensors include a 3D camera, a 2D laser scanner, as well as 4 ultrasonic distance sensors, one on each corner. Using these sensors in combination, the chair builds up a virtual map of its surroundings. Using a people tracking algorithm from our partners at RWTH, the control system identifies humans and tries to predict their trajectories. The user pushes the joystick in the direction they want to travel. The sensors feed in information about obstacles to avoid. The system can then formulate a path that avoids any obstacles, but still generally travels in the direction the user requested. What's new about our approach? At the UCL Pamela lab, we studied how the presence of a robot wheelchair affects the movement of a crowd of people. We used data from these experiments to better predict how a crowd of humans behave. Instead of just seeing them as obstacles, our algorithm treats humans as moving agents with their own intentions. We have also explored different ways of combining the input from the driver with the information from the algorithm. Previous research focused on linear blending, where input from the user and algorithm is combined in some proportion. The output velocity is essentially an average of the input from the user and the output from the route planning algorithm. This is a bit like having two hands on the same steering wheel, and crucially does not guarantee the chair won't collide with obstacles. Instead of linear blending, we use probabilistic shared control, PSC. PSC creates two sets of probable trajectories. One based on the user's input, where velocities that best match their intention are given a higher probability. The other based on a set of velocities from the route planner, where safer velocities are given a higher probability. By combining these probabilities, a suitable output velocity is chosen that better agrees with the user's intended trajectory. Our experiments show PSC performs better in moving environments when compared to existing methods such as linear blending, and resulted in fewer collisions in our simulations. Another element of the project is our attempt to take a user's physical abilities into account when interpreting their input. For example, a user may be able to push the joystick harder in one direction than another. Using a probability distribution, these restrictions can be considered when trying to decipher a user's intent. By adapting the system to a user's specific requirements, any physical restrictions they have can be accounted for and their driving experience can be improved. Throughout the project, we've also developed a framework to ensure ethics are considered. When proposing a system that has the possibility of restricting a user who already has limited agency, this is particularly important. To address this, we are fitting a black box that records all user input as well as data from the onboard sensors. From this data, we can analyse points of disagreement and ensure the system was justified in deviating from the user's intended path. For more information about the CrowdBot project, check out crowdbot.eu.